Okay, so what we're going to do now is show you the power of the calculator. We'll use it more and more and more, and we're going to talk about central limits theorem and how we can apply it. Now, it does apply the central limit theorem for sample means to uniform distributions, as long as we're going into the means of that uniform distribution. So, study involving stress is conducted among students on a college campus. The stress scores follow a uniform distribution. That's very important. That's why it's highlighted. That'll help us calculate the mean and the standard deviation, with the lowest stress score equal to 1, not 0, 1, and the highest equal to 5. Using a sample of 75 students, find A, the probability that the mean stress score for 75 students is less than 2, and that the 90th percentile of the mean stress score for the 75 students. So a little stop and start, and by the end of this, we'll show you a really, really, really cool way to get letter B and make your life so much easier than it's been. So go ahead. Okay, doing stop and start now. What we know is it's a uniform distribution, so I need to find the mean and the standard deviation. With a uniform distribution, the formula for a mean, and remember what I said about photographing these in the lessons that I've given you and having them in your phone. A plus B over 2. So A is the lowest score, B is the highest. 1 plus 5 over 2 is 6 over 2, which is 3. And the standard deviation is highest minus lowest squared divided by 12, square root. So 5 minus 1 is 4, squared is 16 divided by 12, and then square root it, and I get 1.155. And I put all of that into my sample means normal distribution formula, okay? N is what means normal distribution as opposed to uniform. So I have 3 as my mean and 1.155 divided by the square root of 75, because we always have the square root of n here, like in sample error. Okay, so what do I do now? I go to my calculator. I want the score to be less than 2. So that means that the lower extreme, or the lowest level, is 1, and it can't be 0, because 0 is not on the scale, but 2 is. So the highest is 2 because it has to be less than 2. 3 is the mean. This is my standard deviation divided by square root of 75, the number of people in the sample. And when I punch that into the calculator, it kicks out 0, which means it's impossible. It is not going to happen. Okay? Now, let's go to how we calculate 90th percentile with a calculator. It's a whole new technique. It's really cool. This only works for the normal curve. Okay, so let's be clear about this. That means inverse normal. To find the 90th percentile, and this is a new technique with the calculator, we're going to go to, again, second vars, and I think it's the third one down. It says inverse norm. That means inverse on a normal curve. And if you want to find the 90th percentile, you just convert that to a decimal, 0.90. The mean is 3. The standard deviation, sample error, is the same exact thing. Don't change it. Kick it in, 3.2. How easy is that? So much easier than the way to do it with using just the table. You know, I think it was very important to show you the table and to see not just how we old people used to live, but to get an appreciation for what was involved with it and everything going on, and see some relationships involved there. But now the calculator does make this a whole lot easier for us. Okay, up to the next one. Very, very similar question, okay? Except this time, we're going to change to the 80th percentile. So the first part of the problem is exactly the same. You don't need to redo part A. We're just going to have you do part B. It's the same question as the previous slide. I'm just changing it to the 80th percentile to get you a little practice on that inverse normal curve to find the percentiles. Go ahead. Okay, now I go to 80th percentile, my calculator, inverse norm, which is again second vars, inverse norm, 0.80, because this time I want 80 percentile. Mean is 3, same exact thing for the sample error, 1.155 divided by the square root of n, in this case n is 75, and it tells you 3.1. So life is very, very good using this graphing calculator. It does make life very simple. Okay. Next one. Use the information in example 7.8, but use a sample size of 55 to answer the following things, okay? Find the probability that X bar is less than 7 and that the 80th percentile for a mean of 55 scores. Now, what they're talking about here, example 7.8 is the previous problem, but the difference is that now you get to, instead of grading the scores 1 to 5 on stress levels, it's 1 to 7 on stress levels, okay? So it's 1 to 7. Okay. Just to a little bit of a reminder here in case you're forgetting, is it uniform distribution? Okay, so we find the averages. This time it's going to be 1 plus 7 over 2, which is 4. Okay, and the standard deviation would be 7 minus 1 squared over 12, which is 1.732. Okay, so now you have the mean and the standard deviation, and you can now find the probability that X is less than 7. Go ahead. The sample means are less than 7, okay? Okay, using stop and start. So I did misspeak before. I said probability X is less than 7. I'm not saying that. I'm saying the probability that the sample means is that selected is going to be less than 7. So X bar tilde n, that means we're getting into the central limits theorem sample means. The mean is 4, and this is going to be 1.732 divided by the square root of 55 because we're having a sample size of 55 this time. Second vars, normal CDF. I want to go from 1 to 7 because the score has to be less than 7. Mean of 4, 1.732 over the square root of 65. You put it in and you get 1, which means it's a guarantee to happen. You might say, well, you could get exactly 7, but when you do sample means, it's not going to work out that way. It's statistically impossible. What about finding the 80th percentile for the mean of 55 scores? Well, very similar, but this time you don't do second vars normal CDF, you do second vars inverse norm. Second vars inverse norm, 80th percentile, 0.80. Remember, convert to a decimal. The mean is 1, the mean is 4. And then the same thing for the standard deviation. Sampling error, we get 1.732 over the square root of 55, and that gives me 4.2. Okay? All right. So that would tell you that a score of 4.2 is going to be the 80th percentile. All right. Let's try another one here. Let's see, what do we have for memory? Oh, we got plenty of memory left. Let's try this question this time. Suppose that a market research analyst for a cell phone company conducts a study of their customers who exceed the time allowance included on their basic cell phone contract. That's a no-no, can get very expensive. The analyst finds that for those people who exceed the time included in their basic contract, the excess time used follows an exponential distribution. Now again, that's not a big deal because exponential, uniform, they're all, when you use the central limit theorem for the sample of means, it applies to all of them. And the mean is 22 minutes. Consider a random sample of 80 customers who exceed the time allowance included in their basic phone contract. I underlined this because we don't cover exponential distributions, but they put a little side note in here that from previous chapters, again, we don't cover it in this class, we know that the mean is 22 and the standard deviation is 22, okay? So the mean is 22 and the standard deviation is 22. Those are the values you use when you're figuring out your formula. Okay, let X equal the excess time used by one individual phone customer who exceeds the contracted time allowance. Find the probability that the mean, as soon as you see that mean, that means, okay, I'm going to use my central limits theorem formula, excess time used by the 80 customers in the sample is no longer than 20 minutes. Okay, so that means that we're going to go from 0 is longer than 20 minutes. So that means I'm going to go 20 minutes or more. So this is asking us to find the probability that the means is greater than 20. You don't need to draw the graph if you do it on the calculator. Go ahead. Okay, so We go to second vars. And once we do second vars, we go to normal CDF. Now, it wants to be greater than 20, so the lowest is 20. The highest, see, this time I put in like 1 followed by a bunch of zeros, but you're better off doing 10 to the 99th power, because my answer was actually off by a micro amount, okay? So in here, rather than putting whatever that is, a trillion, billion, whatever, I don't even know, gazillion, I just put in 10 to the 99th, and I certainly don't know what you call that. The mean is 22. And the standard deviation was 22, but I must divide by the square root of the sample size, which is 80. And you pump that into the calculator, and it will tell you 0.7919. 0.7919. So that's the probability, about 79%, 79.2%, 0.7919. Okay? All right. Boy, this is easy on a calculator. Quick. It's a matter of knowing what to put in where, how to input your data. Now, the same exact problem with the same exact numbers you just did, but change the sample size to 144 and find the probability that you're between 20 and 30 and the 75th percentile. Go ahead. Okay. So this time we're going to do second vars, normal CDF. The smallest, the lower limit is 20. The higher limit is 30. The mean is still 22. And this time, because we changed the sample size, standard deviation is 22, but we're going to divide by the square root of 144. And again, that's how I like to input everything. I don't like to convert that to 12 and do 22 over 12. You could, but then if you're used to doing that, what happens the next time you have a square root that doesn't work out evenly? So I just put it in as is, and I hit equals, and it says 0.86234. So that means there's an 86.2% approximately chance, or the probability is 0.86, that the means will be between 20 and 30. Okay? All right. Now, find the 75th percentile. To do that, we just go to second vars inverse norm. That's like the third one down. Second vars inverse norm. So I want 0.75, because 75th percentile, the mean was 22, and my standard deviation over the square root of n, the sample error, if you will. I input as I did before, it'll tell you 23.24. So that tells you that the 75th percentile is the score 23.24. And that makes sense, because when the mean normally distributed is 22, then your 75% is going to be a little bit bigger than that. Okay? All right. So let's go to the next question here. Ready? In the United States, someone is sexually assaulted every 2 minutes on average, according to a number of studies. Suppose the standard deviation is 0.5 minutes and the sample size is 100. Okay? So the mean is going to be every 2 minutes. Find the median, the first quartile and the third quartile for the sample mean time of sexual assaults in the United States. And I want you to keep in mind that the median is the 50th percentile, the first quartile is the 25th percentile, and the third quartile is the 75th percentile, okay? So all you're going to do is use inverse norm for 50%, for 25%, and for 75%. And based on the fact that the mean is equal to the median, it's actually pretty easy to figure out the median. And then after that, find the probability that the sexual assault occurs on the average between 1.75 and 1.85 minutes. Okay. All right. So the first thing that I wanted to do was make sure that you understood how to calculate the sample error here, which is the standard deviation divided by the square root of n. So it's 0.5 divided by the square root of 100, which is 0.5 divided by 10, which is 0.05. That's very important. Otherwise, you won't know where this 0.05 comes from here, okay? Now, the 50th percentile, the mean equals the median equals the mode, which works out to be 2. So we know what that is. The 25th percentile, we'll just do inverse norm, 0.25, mean of 2, and then 0.05. Or you could do 0.5 divided by square root of 100. You get the same exact thing. And the calculator tells you 1.95, no, 1.97, so that's the 25th percentile. For the 75th percentile, inverse norm, remember it's always second VAR's inverse norm, 0.75, mean of 2, 0.05 for my standard deviation sampling error for the means theorem, and I get 2.03. That also shows you, by the way, the symmetry of the normal curve, because this one is 0.03, the 25th percentile is 0.03 below the normal curve, and the 75th, which is 25% above the normal curve, is 2.03. So in each case, that 25% amounts to a 0.03. The big rectangle's there because there's a question underneath about sums and central limit theories and sums. We don't get into any of that, so we'll skip it. And we'll go to part C, which says between 1.75 and 1.85, and we'll just do the normal CDF button. So second VAR's normal CDF. The lowest is 1.75, the highest is 1.85, the mean is 2, and my standard deviation factor is 0.05, and that gives me 0.0013. And that's it. I'm all done. Isn't this easy with the calculator? I sure hope it's as easy for you as I have found it to be for me. I used to use tables all the time. Now we're doing it with calculators. Life is good. Okay. You're up. Based on data from National Health Survey, women between the ages of 18 and 24 have an average systolic blood pressure of 114.8 and the standard deviation of 13.1. Systolic blood pressure for women between the ages of 18 and 24 follow a normal distribution. Okay, so we're not talking about sums of means or anything here yet. We just seem to be doing normal work. Oh, see, part A doesn't use means, part B uses means. So part A is going to use a regular formula for the standard deviation, and part B will get into that alternate standard deviation where you divide by the square root of n. Okay, you're up. I gave you enough hints. Okay, so second VAR's normal CDF, 120 is, it wants it to be greater than 120, so the minimum number is 120. This is what I told you. I type in now 10 to the up arrow 99. That's the greatest value that your calculator will handle. 114.8 is your mean, and 13.1 is the standard deviation. And just hit enter, enter, and it'll tell you that the probability of that is 0.34570. Okay, great, no problem. Now the next one, however, well, let me just show you the note I have on this. This is a normal distribution situation, not a mean distribution. So the standard deviation is what it is. There's no need to divide or change it. But the next one says that their mean systolic blood pressure. So we're getting into means. That's why I underlined it. And for part B, this is a mean normal distribution. So you must adjust the mean and the standard deviation. So now I'm going to get second VAR's normal CDF, 120, 10 to the 99th, 114.8. But I have to now divide the 13.1 by the square root of 40 for the 40 people sampled. And that is 0.00603. So notice how much less likely it is that the means of the population is going to be in there. Okay? Person, not so, that's much more likely than the means of all the people. All right, so what's the biggest thing we did today? We learned the power of this calculator. Make sure you have gotten your hands on one. You can continue to do this with the tables, but boy, oh boy, is it a lot harder and a lot of work. How do you use a graphing calculator to solve a normal distribution situation? Second VAR's, normal CDF, enter the information they give you. How do you use a graphing calculator to solve a mean normal distribution situation? Same exact way, except with the standard deviation, you got to divide by the square root of n, where n is the number of the sample size, how many are in it. What's the key difference that you must remember between the two above? It's that dividing by the square root of n on the standard deviation. And for that, you see, is it about means or is it about a single normal curve for just a particular score? And then how to use a graphing calculator to find percentiles? That would be second VAR's inverse norm. So that sets you up with, I think, everything you need to know with central limit theorem applications and using the calculator Have an awesome day. Quiz time after this.